On behalf of Partners in Project Green, I would like to welcome you to our monthly series of green technology webinars. For those of you who might not know, Partners in Project Green, developed in partnership with the Toronto and Region Conservation and the Greater Toronto Airports Authority, is a growing community of businesses working together to green their bottom line by creating an internationally recognized eco-business zone around Toronto Pearson Airport. We offer many resources to help companies along their journey to sustainability. For more information on our programs, trainings, events, and much more, please visit our website at www.partnersinprojectgreen.com. As for today's webinar, we are fortunate to have with us Jan Buick, President and CEO from European Power Solutions, calling in from Mississauga this afternoon. Over the past 20 years, Jan has engineered, project managed, and directed sales and marketing responsibilities for more than 100 CHP district energy and other distribution generation projects currently in operation across Canada. Jan received a degree in mechanical engineering from the University of Utrecht in the Netherlands, where he also wrote a thesis on the use of landfill gas for power generation applications. Jan is a former director of OSEA and the CDEA, holds a director position with the Association of Power Producers of Ontario, and is chair of WAD Canada. Thank you, Jan, and I'm now going to hand over the presentation to you.
Cindy, thank you very much for the introductions. Good afternoon, everybody. Thank you very much for taking the time today to listen to my presentation and follow this online about cogeneration. We do have a lot of material to cover, so I may as well immediately start with the presentation. A little bit about European Power Systems. We are a company that specializes in CHP, also referred to as cogeneration solutions, and are quickly establishing ourselves as one of the leading organizations in Canada specialized in the application. Our business has four legs. Our core business is the supply of pre-engineered packaged CHP systems, ranging from as small as 30 kilowatts to as large as 4.4 megawatts. In the 30 to 200 kilowatt range, we offer the capstone microturbines. From 60 kilowatts up to 500 kilowatts, we can offer packaged cogeneration systems with MAN gas engines, and then for projects larger than 500 kilowatts, we utilize the Jenbacher gas engines. Very important to our business is the service, operation, and maintenance of these installations. It's absolutely critical for the success of cogeneration systems that they run they're supposed to run. So our service support to make sure that customers achieve the maximum availability of these plants is absolutely critical to the success of these systems and the success of our business. We also bring to market exhaust emission control technology, especially in Ontario. The emission requirements are very tough, and there are no reciprocating engines that are used for non-emergency power that can get away with running without emission controls. So we also include with our systems and also offer it for existing sites the emission control, the cleaning technology to get the exhaust emissions within the current Ontario regulatory requirements. And then the last part of our business is system management. As we are starting to see more sophisticated power generation systems, we also recognize that the cogeneration systems we bring to market do need to become more flexible in the way they operate, need to start responding to changing market conditions, changing electricity and gas prices, and need to be optimized to maximize the running time where they can generate power when it's cost effective to generate power, and be shut down when it's not cost effective to produce power. If we look at our product portfolio, on the reciprocating engine side, this goes from 100 kilowatts up to close to 4.4 megawatts. So you can see in the second column the sizes, 100 kilowatts, 160, all the way up to 4.4 megawatts. You can see the thermal output, the total output, and then you can see that the system efficiency from close to 35% for the smaller units up to better than 45% for the larger machine. If you combine that with the thermal efficiency from the heat recovered, you can see here that the total system efficiency when running in cogeneration mode, where you produce power as well as heat, that generally can hit about 85%, 84 to 92% of the energy input is actually used where these systems are being applied. Capstone microturbines come in three sizes. The smallest one is 30 kilowatts. Next one up, 65 kilowatts, and then the largest microturbine is 200 kilowatts in power output. Now we can combine as many as 5 of those 200 kilowatt machines into a single module. It's about a 30-foot long containerized unit, so it's similar to a ISO shipping container, and we can install 3, 4, or 5 of those microturbines in a package like that to get a 600, 800, or 1,000 kilowatt power module, and by doing so effectively can offer a microturbine based power module that is 1 megawatt in size. Our core expertise, we would refer to it as the gas to wires business. The picture here shown is of a biogas plant, and if you look at the back of the picture, this is where you see where the barns are, the stables are, where the cattle is housed. We know nothing about it. You see here the digesters where the manure from the cattle is being converted into methane and fertilizer. That too is not our business. This part within the yellow circle, that's what we consider our core business. When gas is made available, we can turn this gas into power and heat and connect this to the grid, connect this to buildings. That is what we do as our business. It could be for landfill applications, biogas, natural gas-fired cogeneration. It's the gas to wires. That's what we know. That's what our business is all about. So today, I would like to talk about CHP, combined heat and power, CCHP, so that's combined cooling, heat and power, as well as CHEP, and that's combined heat and emerging power. I'll be talking about some technology options. I'll be talking about the financial performance of CHP in today's environment, and I will be providing some project examples, and then we'll open the floor for some questions. So let's talk about the introduction to the various technologies. So the official name, CHP, CCHP, and CHEP. We also refer to it as cogeneration, trigeneration, and then combined heat and emergency power. The basics of cogeneration are in fact, very straightforward. Here's a typical schematic of a cogeneration plant. You have the natural gas, which will flow to the engines. In this case, we're showing 2 engines here. So natural gas is being combusted in the engine that will then produce, it will drive a generator that will produce electricity, and that electricity then can flow either into the grid, or it can be used within a building, within a factory, to displace power that otherwise would be purchased from the grid. Then when the engine is producing power, it will also produce heat, and it will have a few circuits on the engine where heat can be recovered. It would be from the engine jacket water, oil cooler, and intercooler. That's heat that typically is available in the form of hot water. And this loop here is where this hot water would be recovered from those circuits. Then there's also heat in the exhaust, and that heat can be in the form of hot water, but could also be in the form of steam and some other sources. So in this case, we're showing a diagram that produces hot water as a byproduct from producing power. So hot water here picks up the heat from the engine jacket water, oil cooler, and aftercooler. It then will flow to another heat exchanger that will pick up the heat from the exhaust, and then the water, which typically is at about 90 degrees Celsius, 190 to 200 degrees Fahrenheit. That hot water will then flow to the customer. So this is where the hot water can be used on site. It can be combined with the boiler system. So typically the cogeneration system will produce the heat. If there's more heat required than what the cogeneration system produces, then boilers can supplement the additional heat required. It's also possible that if you want to produce power, but there's no demand for heat, that the heat then, rather than being destroyed, that the heat is being stored in a buffer tank, which would allow you to produce power at one point of the day, store the heat, and then maybe at night when the engine is not running, still use that heat for heating the building or the facility where the cogeneration system is located. It is also possible to use the heat to produce cooling. And I will not get into the intimate technical details of the absorption chiller here, but this is called absorption cooling. So you see the exact same system as what was shown on the previous slide, where heat is being recovered from the engine. That heat can be used again for heating up a building or providing process heat. There are many circumstances where in the summertime there may not be any heat demand in the building itself, and rather than wasting this heat, it could also be utilized to drive an absorption chiller. So here you can see how the heat from the engine actually will be utilized in the absorption chiller. In the absorption chiller itself, you have the section where heat is being introduced. Then you have the section where the chilled water is being produced to provide cooling to the host, and then there's a cooling tower that will facilitate this process. Essentially, within the absorption chiller, there's a mixture of lithium bromide that will go through liquid and gaseous phases, and as it goes from one phase to another phase, that's when heat is being introduced or heat is being removed from the process, and that then provides some cooling energy using the waste heat that is available from an engine during times that heat may not be required for the building the engine is located. Now, it's not only hot water and electricity that a cogeneration system can provide. If you look at electricity, we typically see electricity being delivered at voltages for the smallest units We can go to 208 volt as the generation voltage. We can go, the highest that I've seen for our types of systems is about 13.8 kV as the generator voltage. Most of the applications in Ontario would see generators below 2 megawatts to run at 600 volts and larger ones at 4160 volts. If you happen to export power into the grid, then this voltage could be increased to 13.8 to 27 or 44 kV as required to the, for the grid that you're connecting to. We can produce steam. About half the heat of an engine is available from the exhaust. So steam pressures up to 200 pounds pressure is not uncommon and is easily produced. Hot water is typical for applications, and we would generally run systems with a water temperature that's around 90 degrees Celsius. We also can produce hot air. Hot oil can be at high temperatures, significantly higher than the hot water temperature. Again, in that case, we would recover the heat from the exhaust to produce this hot oil. You've heard me mention emergency standby power, combined heat and emergency power. A few years ago, the Canadian code that governs emergency standby power, CSA 282, was amended to allow for the use of natural gas as a suitable fuel to provide emergency power. So today, the natural gas infrastructure is considered to have the same reliability or even better reliability than on-site diesel storage. So what this has allowed us to do is to not only provide engines that run on natural gas and qualify for providing emergency standby power for what would be considered life safety loads such as elevators, fire pumps, etc. But that we also can provide a cogeneration system where the unit would provide power and heat to a building during normal operation, and in the event of a power outage can provide emergency power. And in a situation like that, the building no longer requires the standby diesel on site. Another source that can be utilized is the CO2 in the exhaust. So for greenhouse applications, it's actually possible to clean the exhaust to a point where the exhaust is clean enough to be directed into the greenhouse, where then the plants absorb the CO2, and in that case, the CO2 will be used to increase the production of tomatoes, peppers, cucumbers, or in the case of flowers, impact how fast the flowers grow or when the flowers will bloom. And that we talked about earlier, we can also produce cooling from a cogeneration system. So let's look at some of the technology options. If we look at the three types, we have packaged cogeneration modules, typically smaller than 500 kilowatts, typically used for indoor application. We can also put those systems in a container or custom outdoor enclosure. So we can have complete packaged systems up to 1.4 megawatts that can be supplied for outdoor installations. And they also have ultra-low noise options of 55 dBA at 10 meters, which is quite suitable for urban areas where noise is of extra concerns. And then for larger systems, and that's typically 1.5 megawatts and up, we can also offer prefabricated systems, and we offer those for units up to 4.4 megawatts, or multiple units could go to 20, 30 megawatts or even larger. So if we start with the cogeneration module, the smaller units, this is what a module like that would look like. So if you see here the generator set, on top of the generator is the air intake filter where air is being drawn into the engine. It's mixed with the gas for the combustion. So you can see that at the front of the unit, here's where the gas inlet for the unit is. Then there's piping through the base of the unit, and then here's where gas is being mixed with combustion air for the engine to then run on this fuel. In the base is where the exhaust heat recovery is located. Batteries, battery charger are also incorporated in this kit. And if you then look at the front of the unit, you see how it's a complete packaged unit that includes all the pumps, all the thermostats for a complete CHP system, gas inlet, exhaust outlet. So after the heat's being recovered from the exhaust, this is where the exhaust is taken from the unit. We have the heat exchanger that interfaces between the engine circuits and the building. Then you have one pump that circulates the water with the building boiler loop. Here's another pump that is used for interface with the radiator, so when the building does not utilize all the heat that is available from the cogeneration unit, this large pump here will circulate water to a nearby radiator where the cooling takes place. And then here's a smaller pump that would circulate the water for the intercooler, which often is at temperatures too low to be utilized. So you get a complete system with all the connections ready for interconnection to the building system, hot water to the building, hot water to the main radiator, hot water to the intercooler radiator, and you get a complete package system that is ready for interconnection to the building services. Now, to go back to the previous slide, you see that there's a large frame that's being utilized to build this machine. And the reason we do that is because the frame then also can be used to mount a sound enclosure. So if you install something like this in a building, you really would like to keep the noise to an absolute minimum. And by including the ability to add these sound panels, we can make the machines very quiet for installation inside the building, inside boiler rooms. We also can provide those machines, the smaller ones as well as the larger ones, up to 1.4 megawatt as a complete packaged containerized system. And essentially, what we bring to market is a complete solution where we look after everything that's in this box. What the customer needs to worry about is the gas connection to get gas into the machine, the electrical connections at the generator breaker, so that is inside the container itself, and then the hot water connection where the hot water would interface with the building. We would ship, deliver, offload, and assemble the complete system like this and leave the customer with those 3 connection points. So we look after the performance of the machine, the design of the system, make sure that we provide a complete, fully integrated system where the design of the system is proven based on hundreds of similar identical units supplied into other projects. It really makes sure that the system has maximum reliability. It really lowers the engineering and installation costs, and it also results in shorter project timelines. And we also achieve that the systems have very little issues that need to be resolved after a plant is started up. Now, for larger projects, of course, they don't fit in a custom container or custom enclosure like that. So that's where rather than custom designing every system, we have moved towards a process where we offer prefabricated CHP systems. And this picture shows the different components that typically are included in a prefab cogeneration system. So if we go around the perimeter here, we have the two ventilation ducts and silencers where air to cool the enclosure for the engine is drawn to the enclosure. We have the exhaust stack that emits the exhaust into the air. We have an acoustical enclosure that is designed for a noise level of 75 dBA at 1 meter. Again, we have the connection points where we define our basic scope and from where the customer takes it. So we have the natural gas inlets, and we have the hot water connections where we deliver hot water to our customer. There is always a wall that can be removed for major maintenance, for major overhauls. If equipment needs to be removed from the enclosure, then it's easy to do with a removable wall. It shows here the control panels for a system like this. We have the exhaust silencer that is part of the stack. We have the exhaust heat recovery equipment. We have the emission controls. We have oil tank, urea storage. The urea is, by the way, required for the emission controls to meet the current Ontario emission regulations. And then we have the heat dump radiators that are required to provide proper cooling for the engine in the event the building does not utilize all the heat provided. Now, there are significant benefits of working with a standard layout, with prefabricated systems. It really defines where the interface points are, and it provides an optimum layout. We make sure that there's enough space around the machine for service. We work with modular building blocks that we can work with fewer or multiple units and basically scale it up or scale it down as required to address the site-specific requirements. It really minimizes the site work. Everything shows up as prefab components that need to be assembled and uses a well-established design for this type of installation. It really minimizes. We strive to eliminate engineering and installation mistakes, and it ensures maximum system performance and reliability. So if we work with these standard products, this is how we would build up a cogeneration system like this. We would start by starting with the assembly of the sound enclosure. Then once the enclosure is assembled, we start mounting the first exhaust silencer. Again, it's done to keep noise inside the enclosure. Then we position the exhaust heat recovery equipment. Then on top of the exhaust heat recovery equipment is the SCR system, the exhaust cleaning equipment. Once that's done, the filter box and the second silencer are installed. We then, and I forgot to mention, the engine is also moved in the enclosure. So at this point, the engine is in place and most of the key components are installed. Then the enclosure is closed up, and some of the main piping, interconnecting exhaust piping is installed, and then the ventilation ducts are and silencers are mounted on top of the enclosure. Then the oil tank, urea tank, radiators, control panels are positioned, and then once that all is in place, then the interconnecting piping is installed, the welding of the exhaust piping is done, cabling, control wires are installed, and once that's all complete, the system is ready for commissioning and handover. Now, I keep referring a couple of times to the sound enclosure. Very important because it provides the optimum environment for the engine to operate in. It keeps the noise in the enclosure, and it also separates engines from other engines, so a service technician can work on one engine without being bothered by the noise from engines that are nearby. And this here shows how this would work within a indoor installation. So you have the enclosure that houses the generator set. You have the air inlet with the silencer. You have variable frequency drive fans to control the temperature inside the enclosure. You have lifting beams over top of the engine to make sure that the heavy components can be easily lifted. And this provides the optimum environment for an engine to operate in. And that's the end result. A properly designed and built CHP system that can work as intended for the next 20 years or longer. Now, you can also do this for outdoor applications. At that point, the exhaust system and the exhaust cleaning equipment, which would, for an indoor installation, sit outside the enclosure. This is now installed inside the enclosure. And this is a drawing that shows where the different components are when it's installed inside an enclosure. So you see the exhaust system, the cleaning system, the heat recovery system, and the stack. You have here the oil and urea tank. And if you then look at what this looks like in real life, then you get something like this, where complete, in this case, a 3.3 megawatt system installed in a outdoor prefab enclosure. So looking at this, again, the approach is similar to our containerized systems. We will supply, deliver, offload, assemble complete systems and leave the customer with the 3 connection points: gas inlet, hot water outlet, and your electrical connections. And the result is that it minimizes, hopefully eliminates engineering and installation mistakes. It lowers engineering and installation cost. You know it's designed right, and the system reliability is absolutely phenomenal when you approach projects like this. Also mentioned microturbines. So switch gears here for a moment. Very unique technology. Claim to fame is a one part that moves, and the one part is this shaft here, where you have the turbine and the generator all connected on one part that spins at about 96,000 RPM. Units are used for parallel generation operation. They can run in standalone mode, so they can also run independent of the grid. They cannot be used for emergency standby operation. So when looking at microturbines, if emergency standby as defined by CSA 282, if that is required, then microturbines cannot be utilized because they are not recognized by CSA 282 to meet their criteria. And the main reason is that it will take some time for the microturbine to start up, where CSA 282 does require that a unit is ready to accept load within 15 seconds from a power outage. This is what the microturbine looks like at the inside. It's basically, in this case, a 65 kilowatt unit. It's like an oversized refrigerator. The top section is where the microturbine is located. with the microturbine itself, the generator. The bottom section is where the electronics are, the batteries, the battery pack, the load control module, and yeah, these units are very compact and can easily be mounted inside a building, in a basement, on top of a roof, very flexible, and because of their compact size, are very well suited for installation in hotels, apartment buildings, YMCA's, etc. That claim to fame, very, very low emissions. Where reciprocating engines today do require the exhaust cleaning, as I talked about earlier. Microturbines have extremely low emissions, do not require the additional emission controls, and can be installed without the need for any additional emission control requirements. Additional benefits are that the unit does not require any lubricants, no antifreeze, no oil. It's basically the air bearing is what where the unit spins. There's far fewer parts that that require maintenance than what you would see on a reciprocating engine. Like the reciprocating engine, you can see that you can do cogeneration with the microturbine. So looking at the right part of this slide, the bottom section here is the microturbine. Because there's no oil and cooling circuits on the microturbine, all the heat is present in the exhaust. So that is also where the heat recovery takes place. And with a unit like this, it's at the top where the exhaust outlet is. This is where we then can mount an exhaust heat recovery unit and have a module that is fully integrated. Gas supplied to the unit, electricity is being provided, and then heat in the form of hot water comes from the exhaust. And again, we can achieve about a 85% total system efficiency with those microturbines. So let's take a look at the financial performance of CHP systems in today's market environment. We see that customers are seeing electricity prices being high and expect them to continue to go up in years to come. We also see that there's a change in attitude towards natural gas prices. A few years ago, when natural gas prices had first come down, the general thinking was that gas prices would be volatile for some years to come, and we see that perception is changing. That more and more often there is a recognition that natural gas prices are low, and there's an expectation that natural gas prices are going to stay low for some years to come. So that is starting to create the environment for natural gas-fired cogeneration to become a viable investment again. And this is what we would do to help a customer investigate the possibility of cogeneration at their facility. And typically we would be looking for a 12-month overview of electricity and gas bills. So the natural gas consumption in cubic meters per month, electricity kilowatt hours demand in kilowatts, what the monthly costs are for electricity and gas. And with that information, we can then start to come up with a preliminary analysis of what the real possibilities are for cogeneration at this particular facility. So with this information, we would do an assessment of the current energy costs, and this is graphical representation of a real customer in Ontario, where before installing cogeneration, they would see an energy cost that is typically around $100,000 per month. They would see about 40,000 of this energy cost being natural gas, and then the remainder, $60,000 to $80,000 per month would be their cost of electricity. So today, this customer would see a annual energy cost for natural gas and electricity to be just over $1.3 million. If they would proceed with a cogeneration system, you can see what happens. Most of their costs now, or the energy now, comes from CHP. So in electricity right now, you see that most of the electricity produced now comes from the CHP unit, and a little bit comes from the grid. If you look at what happens with the heat supply, most of the heat supplied throughout the year now comes from the CHP unit, and then you have the remainder being supplemented by the boiler system. So what their cost picture looks like after a cogeneration system would be installed is that before cogen, the energy costs would be $1.3 million. After installation of CHP unit, their costs would have gone down to just under $800,000 per year. So their net savings after implementation of a cogen system would be about $550,000 per year. So it, in this case, we were looking at a 1 megawatt machine, and we estimated a capital cost that was in the $2 million range. So they will be looking at a better than 4-year simple payback on a $2 million investment. And so if you look at what the possibilities might be for your facility, the information we require typically is 12 months of gas usage and gas billing. Same for electricity. We'd like to know what your electric load profile looks like. Are you running 24/7, 16 hours a day, 5 days a week? We'd like to know what the heating system looks like. Is it process heating? Is it steam, hot water, hot oil, air? And with that information, we can then provide a feasibility analysis. We can come up with a preliminary system recommendation, provide a financial model, and then work with the customer towards what the next steps are to work towards implementing a project like this. So let's look at some project examples from around Ontario and elsewhere. You've heard me talk about combined heat and emergency power. This is a good example of what this could look like. This is a unit that was installed on Bloor Street, right downtown Toronto. The picture here shows the crane lifting a containerized unit to the top of a 19-story building, and this unit will provide power and heat to this apartment building. It's a building owned by Toronto Community Housing, and by putting in the cogeneration system, they no longer require a diesel engine on site, and the system provides power, heating, as well as emergency power to this apartment building. Similar approach for a unit installed at Villa Colombo in Vaughan. Again, it's a project where initially the the building. It's a long-term care facility. Would have installed a standby diesel. By investing a little more money and proceeding with a natural gas-fired cogeneration unit, they no longer need the diesel unit, and again have a cogeneration system that provides power, heat, as well as emergency power to this facility, and no longer have the diesel engine on site. Next project is a hospital application. This project is at Queensway Carleton in Ottawa, and it's a good example of how a heat recovery system can be optimized for a specific site. So in the top picture, you see the engine sitting inside an enclosure inside the boiler room. This here is the exhaust heat recovery, where steam is being recovered at 100 pounds pressure. So for this building, the engine delivers hot water to the from the engine coolants, oil coolant, aftercooler circuits, and delivers steam at 100 pounds pressure from the engine exhaust. Also unique here is that the system not only runs on natural gas, but also has propane as a backup fuel. The hospital already had propane as a backup fuel for their boilers, and asked if they could use that same propane as a backup fuel for the cogeneration system. So in the worst case scenario, where there's a natural gas interruption and there's a power outage, the hospital can still run this unit on propane and deliver power and heat to the hospital. Next example is a tri-generation or combined heat, cooling, and power project at the Ontario Police College in Aylmer. And this is where, again, it's a outdoor enclosure, complete cogeneration system in a box. And in the summertime, heat from the engines will be used for absorption cooling. So this unit will provide power, heating, and cooling to the police college. And then the last reciprocating engine example is the greenhouse application, which I mentioned earlier. This is a 12-megawatt project in Kingsville, just east of Windsor, close to Leamington. And this is where, in addition to power that goes into the grid, heat that goes to the greenhouse or goes to the buffer tank, the exhaust is cleaned and is also being used to improve or increase the productivity of the greenhouse. And what I talked about earlier, that heat that is not utilized when power is being produced, that can be stored in buffer tanks. This shows to what extent you can go with this thermal storage. At this site, in combination with the 12-megawatt cogeneration plant, the greenhouse installed 4 tanks of 2.3 million liters each. So we're talking close to 10 million liters of thermal storage, where during the day when the greenhouse may not be able to utilize the heat, but the plants do want the CO2, the engines can run. CO2 will go to the greenhouse, power will go into the grid, and hot water is stored in the buffer tanks, that are shown here. And at night, when the engines are not running, the hot water is drawn from the tank to provide the heating to the greenhouse. Talk a little bit about microturbines. Here are some of the typical microturbine examples. This is a office tower facility where as many as 12 microturbines are installed on top of a building. Microturbines, because they have less noise and vibration to deal with, are especially well suited to be installed at higher levels in buildings. Reciprocating engines have a bit more vibration to contend with, and as you get higher up in buildings, it gets a little trickier to make sure that no nuisance noise and vibration is transmitted to the building. So for high rises, higher buildings, microturbines may well be a better fit for this type of application. Hotels, very good opportunity for microturbine cogeneration systems. This is a site with a system with 4 60-kilowatt machines at the Ritz-Carlton Hotel in San Francisco. Supermarkets. Here's an example of a system that provides cooling, heating, and power for a supermarket. Again, very good example of a microturbine application. Schools, whether it's high schools, colleges, universities, they too might be fantastic sites for implementation of a microturbine cogeneration system. There's 16 microturbines installed at the Ronald Reagan Presidential Library in California. Again, an example of where microturbines could be applied. So in conclusion, market segments cover pretty much everything you can think of, whether it's retailers, hospitals, office buildings, telecommunications, hotels, government buildings, schools, airports, landfill sites, biogas applications. You will find opportunities for cogeneration pretty much everywhere. And looking forward, we strongly believe that there is a significant market opportunity for on-site cogeneration, that the economics for self-generation and displacing power and heat for your own use are very good. And we would like to hear from you to help you look at what the possibilities might be for your facilities. And with this, I would like to open the floor for questions, as we have a few minutes left to address any questions that may have come up. Thank you.
Thank you, Jan. This was a very informative presentation. We'd now like to take time for questions. If you have a question, please type it in the chat box, and I will read it to everyone to hear. And we're just waiting to see if anyone has any questions. Well, Jan, it looks like everyone appreciated the clarity of your presentation. Oh, here we go. There are some questions. The first question is, what is the current OPA position on self-generation regarding the debt retirement charge?
It is my understanding that debt retirement, that you do not pay that on self-generation, but I do not know that with certainty, to be honest.
The second question, what are the government incentives available for these generation sets?
I wouldn't count on it. There have been incentives offered over the past years through cogeneration programs such as CHP request for proposals, as well as a CHP standard offer program. Those programs have ended, and given that the government's currently considering the power situation in Ontario such that the perspective is that there's a surplus of power, I do not expect there to be direct incentives available in the upcoming years for on-site cogeneration, self-generation.
The next question is, for heat recovery, do you use condensing heat economizers, which are much more efficient?
We do. Certain sites. Most sites, they will cool the exhaust to 120 degrees Celsius. We also have applications where the exhaust is cooled to 50 degrees Celsius, and it really depends on how much of that lower temperature heat can be utilized. But the answer is yes, we do use the condensing heat recovery as well.
The next question: what would be the cost in an average for a unit?
Sorry, what was the?
What would be the cost for a unit, an average cost?
There's no average cost for a unit. What we see is that as you go larger, that the relative cost per kilowatt goes down. So when you're in projects of 1.5 megawatt and larger, you may build a project for maybe $2,000 per kilowatt. If you're in projects below 500 kilowatts, you quickly can see $3,000 or $4,000 per kilowatt as the installed cost, because the economies of scale are not as good for the small units. Yeah, there's still the same engineering, the same discussions with utility that are required for smaller units as you do for larger units.
The next question: how much does the tri-gen add to the cost versus the comparable cogen unit?
On a 1 megawatt machine, it could add $200,000 to $250,000.
The next question: what is the current cost of maintenance for the microturbines? In the past, at 40,000 hours or so, you had to replace the turbine core.
Yeah, and we still do. At 40,000 hours is when the turbine core would be replaced, and we would offer complete maintenance programs with guaranteed maintenance costs for microturbines that are at about a penny per kilowatt hour for up to 80,000 hours. So it would be a 10-year contract. Actually, I think it's a 9-year contract or 80,000 hours, whichever comes first, at about a cent per kilowatt hour.
And the next question: in 2012, so far, there have been over 124 hours where the price of power has been below zero. This is an increase from the last year. How does that affect the financials?
That makes it impossible to develop a project based on the market price of power. Unfortunately, we have a market in Ontario that does not reflect the real cost of power generation, and the end user pays a cost of power that not only includes the market price of power and then the cost of transmission and distribution, but they also pay the global adjustment, which is the cost of the contracts that have been signed with various power generators. So the end user sees the real cost of power. The market does not reflect the real cost of power, which means that for project opportunities in Ontario, it is today not possible to develop projects based on market pricing, because the end user does see all the costs associated with the generation of power. It is very attractive to develop projects based on displacing power that otherwise would be purchased from the grid.
We have a question about where can we get a copy of the power presentation. As far as I know, this webinar is being recorded and it will be posted on the Partners in Project Green. I think that the person who is asking this question, you could just go ahead and contact Jan and see if you could perhaps get his PowerPoint presentation. That will be between the two of you, I think, right?
Actually, I can confirm this. on the slide, I assume it's still visible to the people online,
All right.
is my email address. So send me a quick email. I will forward the presentation to you, and I'm not sure if this also will be posted online, but yeah, it will be available to those who are interested in the presentation itself.
Thank you. What's the typical payback, and I'm assuming that's period, or range that you see?
We see smaller projects, and I'm referring to smaller as being below 500 kilowatts to be yeah, a little better than 7 years as a simple payback. Larger projects quickly see paybacks that are better than 5 years, and we see some projects where the site conditions are favorable to get into the 3 or the 3.5 year simple payback. So we see returns on investment that we believe are quite attractive and would make it viable to invest in this type of technology.
Do you anticipate there will be disincentives from the government if too many units go in?
Who knows? Yeah, there's always a moving target, and I do view this as windows of opportunity. I've been in this business for the past 20 years, and we've gone through a few cycles of incentives for generation, to programs being canceled, to behind the meter being very attractive, to new incentives. So this will be a dynamic situation that will change over time, and yeah, I cannot comment on whether there will be disincentives or not.
Well, thank you. It seems like all the questions have been asked. So in conclusion, partners in Project Green, along with our webinar partners, Greening Greater Toronto, Better Building Partnerships, and the Canada Green Building Council, Greater Toronto Chapter, including our utility partners, Hydro Brampton 1, Enbridge, EnerSource, Toronto Hydro. Thanks you for joining us this afternoon. We hope that you found this information valuable. If you have any questions, feel free to contact us at info@partnersinprojectgreen.com. And please join us for our next webinar scheduled for November 15th at 1 p.m. Thank you very much, everyone. Goodbye.